nonlinear, or as discrete or continuous, as time invariant or time varying, lumped parameter or distributed parameter. So for each of these categorizations, one aspect of the system is considered. Just a moment.
Ma'am, your screen is not showing.
I know, because somebody wanted to enter. I want to admit. Can you see it now?
Mm,
Yes, ma'am.
Uh, Students entering, actually, I have to admit them, so I'm just minimizing. There was some problem with, I couldn't access the previous link for some reason, so I had generated a new link. That is why I'm just, trying to give some allowance for joining. But anyway, now I'll be starting, and possibly I will not be admitting any more students, because that's going to be a problem. So as I say that, again, somebody wants to enter. Okay. Let me put this notification to one side. Is that possible? Anyway, so now can you see the screen? That is number 57, I'm showing,
Yes,
right?
yes, ma'am. Yes,
Right.
ma'am.
So now the classification as static systems or dynamic systems is what we are going to see first, right? So on the left hand side, you see those are the properties of static systems. On the right hand side, we find the properties of dynamic systems. Now, as far as static systems are concerned, basically the second point over there, that is, mathematically, if we want to describe static systems, they can be described merely by using algebraic equations. Whereas if you are to describe the describe the mathematical model of a dynamic system, you would have to use differential equations or difference equations. So that is basically the main difference from the, you can say, the scientific point of view. The first point over there, all variables arrive at the steady state instantly. Say, for example, if you are considering a pure resistor, right? So if you apply a voltage V across it, current I is going to flow, and the equation that is going to describe the system is going to be V equal to IR. So over there, you can see that it is an algebraic equation which can describe the system itself. Excuse me. On the other hand, if, say, for example, along with a resistor, I have an inductor as well, then I have to describe the dynamics of the system by using the equation that you see over there. That is V equal to IR plus L di dt. Of course, I and V are functions of time, so those are indicated in the equation that you see on the screen. But over here, you find that the the system is described mathematically by using a differential equation. It cannot be described by using an algebraic equation. So basically, that would mean that a system which consists of a resistor and an inductor, and for that matter even a capacitor, is a dynamic system. So if you look at the variables of interest, voltage and current, you find that in the second case, that is, in the case of a system which is a dynamic system, the variables would not arrive at the steady state instantly. On the other hand, if you look at a system where you have the pure resistor, that is a static system for our example, you would find that V equal to IR, meaning that I would instantaneously reach its value and stay over there. There is no variation of the current. Once the voltage is applied, you find the current at a particular value. Let me admit somebody who has, okay, so no more after this possibly. Right, so if now I ask you to give an example of a static system from the mechanical domain, can you try to tell me what, say, would consist of a static example of a static system from the mechanical domain? Or let me reframe my question. Let us say that we have a mass and a dashpot, right? Or a damper, as you call it. Is that system a static system or a dynamic system?
Dynamic.
Dynamic system, right? Contrary to that, can you, I mean, simplify that and tell me what a static system would be from the mechanical domain if I consider I mean, something similar to what we just stated? I'll repeat my question. We said that a mass and a damper together makes the system a dynamic system, naturally, because you would be requiring differential equations to describe its dynamics, as well as, I mean, if you are applying a force and you, I mean, want to see what the displacement or its derivatives, that is velocity, etc., are, naturally, it's going to be, I mean, described by differential equations, and it constitutes a dynamic system. On the other hand, if I were to name a static system from the mechanical domain, a static system now from the mechanical domain, static system means that you would be able to describe the, I mean, the system itself by only using algebraic relations, as well as you would find that the variables arrive at the steady state instantly. Can somebody try to give me an example of a static system from the mechanical domain?
Ma'am, refrigeration system.
What system? Sorry, I didn't get you. Repeat what you said.
Refrigeration.
Refrigeration. How?
Ma'am, it has no dynamic part.
It has
Pendulum
not.
in a vacuum.
See, whatever you are describing, first of all, let us look at the refrigeration system. It's a very complicated system, and I mean, lots of, I mean, if you were to describe the system, it would be quite a complicated matter. Obviously, differential equations would be required for if you are looking at the thermodynamic, or yes, the thermodynamic aspect or any other aspect of it, the electrical aspect as well. It would be a dynamic system. Several equations, which would be differential equations, would be required. On the other hand, a pendulum again, if you are looking at the pendulum, can you, I mean, sort of try to explain why you want to say it is a static system?
The position in vacuum, the position will be with respect to time only.
But does that, the position is changing versus time, isn't it? Does it arrive at the steady state instantly, as we have stated?
Its output is only oscillations, so it will be in SHM instantaneously.
Oscillations, yes. Oscillations means what? The position is changing versus time, as well as your, I mean, there is a particular acceleration acting on it, isn't it? Would you be able to express its model by using, without using differential equations, that is?
No.
Velocity is involved over there, isn't it?
Can it be any mass at rest on which no force is being applied?
Yes, you are partially correct. If there is a simple mass, force, I mean, not only at rest, but if there is a simple mass, in that case, I mean, that would be a static system, because if you are applying a force, basically, I mean, whatever happens to it will be described by using algebraic equations only. P equal to mf, or whatever you, I mean, notations you use, f equal to ma. Over there, you would find that basically the mass would be considered, a pure mass would be considered as a static system. On the other hand, the moment I have a mass as well as, say, a spring attached to it, or for that moment matter, a damper, in that case, what would happen is that I would have to use differential equations to describe the dynamics. So basically, uh, there are other examples, say for example a simple gearing arrangement, a gear, okay, so over there only the ratio, so it is a static system. No differential equations would be required for, it's a simple conversion. from, I mean, sorry? Yes, constant, something is moving at a constant velocity. If
But ma'am, but then its position cannot be defined at any moment.
In a single dimensional motion.
Hmm.
no, the basic theory is that if you are able to describe the dynamics, describe the model by using only algebraic equations, then it is going to be considered as static, right? So if the, I mean, velocity is constant and nothing else is acting on it, there is no frictional force, etc., etc. I mean, it is that simplified. In that case, you would be able to express it in the algebraic form. But I mean, the first point also must be valid in the sense that all the variables have to arrive instantly at the steady state. So say for example, if something is moving with a constant velocity and then some force is applied on it, naturally it would be accelerating. So in that case, what would happen? The moment it accelerates, I would not, I mean, there would be some transients and then it is going to reach the steady state. It is not, the variables are not going to arrive at the steady state instantly, are they? What I'm saying is that something is moving at a constant velocity is what you have stated as an example. Fine. Now, if a force is applied on that body, what will happen to it? It's going to accelerate naturally, and then it is going to change. The velocity is going to change to some new value, say, right? So, if that happens now, what will happen? I would have to describe the motion by using differential equations. I cannot say that the variables arrive instantly at the steady state value, right? There are going to be some transients involved over there. So in that case, that is why it is not an example of a static system, right? But say, for example, if there is a simple conversion from one form to the other, or say, for example, even in, I mean, say a gear or some component where you see only a multiplication factor. So say for example, I mean, the input is just being multiplied by a factor and you get the output. For that matter, say if you consider an amplifier in the electrical domain, right? So you give a voltage input and the output is going to be a multiplication factor multiplied by the input voltage and nothing else over there. So naturally, if you are considering only the output to input portion of the amplifier as your example, in that case it is going to be a static system. On the other hand, of course, I mean, if you want to see I mean the internal your circuit, etc., and then you want to analyze, in that case naturally uh, you would have to consider the equations, and the equations, if they are differential equations, naturally it will be a dynamic system. So definition of your system and I mean the description of your system, if the description can be made by using a set of algebraic equations only, and your variables arrive at the steady state instantly, in that case the system would be considered as a static system. In all other cases where, I mean, differential equations are required and some transients occur before the steady state is reached, the variable or variables do not arrive at the steady state instantly. Those are examples of dynamic systems. So all control systems, or for that matter, all systems can be categorized into either static or dynamic systems. The next classification that we can speak of is linear system or nonlinear system. So as far as linearity is concerned, you are already familiar with this. That is, linear system is one which obeys two principles that you can see over there. It's written: principle of superposition as well as homogeneity, right? So those have to be valid for a system to be considered as a linear system. On the other hand, any system which does not um, obey the principle of superposition or the principle of homogeneity, or both, those systems would be considered as nonlinear systems. So now if I look at the characteristic of a linear system, it is going to look like the one which is drawn on the left hand side, this one. Can you see the cursor? I hope you can see the cursor. If not, just tell me. So you can see the cursor, right?
Yes.
Yes. So this one, you see that the output to input plot is shown and the characteristic is a straight line passing through the origin. So that would automatically imply that the principles of superposition and homogeneity hold good, or vice versa, in the sense that if the principle of superposition and the principle of homogeneity hold good, the system characteristic is going to look like this. That is a straight, it's going to be a straight line passing through the origin, and that would make the system linear, right? On the other hand, okay, now before I go to the other thing, over here please note something which is very important, that is the axis over here at the output and the input. It is not the time response, mind you. Okay, so do not confuse this characteristic that you see on the left hand side with the time response, which is, say for example, a ramp input or something like that. It's going to look like this, a straight line through the origin, but there it is the response which has been plotted versus time. On the other hand, this characteristic that you see over here, which is valid for linear systems, is a characteristic which is a plot of the output to the input using proper units. So all linear systems would have such characteristics. Okay, and that would that would automatically imply that the principles of superposition and homogeneity hold. On the other hand, if some system, or for that matter even a single component, does not obey either of those principles or both of them, then this overall system would be considered as a nonlinear system. So this, okay. So now, when I say that, I want to emphasize one thing, that is basically if even one component present in the system does not obey the principles of superposition and homogeneity, the whole system becomes a nonlinear system. So when I say a nonlinear system, what do I mean? Again, over here, I have the output to input plots, two plots shown over there, in which you would find that the left hand side plot, that is this one, is a saturation. It is a characteristic which is indicating that saturation has taken place. Why saturation? Because over here you find that starting from here, the 0 0 position, I find initially the characteristic is a straight line passing through the origin, and for a change in the x, that is the input of the system, a proportional change in the output is occurring. So a proportional change in the output corresponding to a change in the input is going to make the system, this portion rather, linear. On the other hand, once an input which exceeds the value, say x0, which is mentioned over here, is applied to the system, what happens is that any change in the input is no longer going to give me a proportional change in the output of the system. The output has frozen at some particular value, that is a saturation value. So in this case, this portion is no longer going to give me a proportional output, and it makes the overall characteristic nonlinear. So you find that in this particular plot that has been shown over here, the characteristic has saturation both on the positive side as well as the negative side, and it is an example of a linear characteristic, a nonlinear characteristic. Now, even if one component in the system has a nonlinear characteristic like this, then the overall system would be considered as a nonlinear system. Similarly, on the right hand side, you find that a hysteresis curve has been drawn over here, something that electrical engineers are very familiar with. The hysteresis again is something where you find that with an increase in the input side, that is over here, say an extension which is shown, there is not, there is no proportional change in the output side. force is the output quantity which has been considered over here. So here you find that in this particular, I mean, characteristic, change in the input, some change in the input is not going to provide a corresponding proportional change in the output. And this characteristic hence is a nonlinear characteristic. Again, in the presence of one hysteresis, at least one hysteresis in the nonlinear system would make the overall system, wherever it is present, it's going to make the overall system a nonlinear system. So systems may be classified as linear or nonlinear, either a linear system or a nonlinear system. For a system to be considered or classified as a linear system, all its components and the overall system itself should be linear. On the other hand, nonlinearity, in case of nonlinearity, one component, even if one component is nonlinear, one or more components may be nonlinear. In that case, the system, overall system, would be considered as a nonlinear system. So
Can
more
we test that the impulse response of a linear system will be constant?
impulse response, sorry.
Of a linear system will be constant.
Yes, but over here we are, mind you, we are not, I mean, going to the response side at all, right? We are, I mean, trying to look at what happens to the output versus the input. This is not a, as I mentioned, it's not a plot versus time. Response is essentially a plot versus time, right? So, I mean, we need not look at
Transfer
the. Mhm.
transfer function of the linear system
Transfer function of a linear system, yes.
will be constant.
No, never. Transfer function of a linear system will never be constant. Say, for example, if you have a system with a transfer function, say 1 by s plus 1, is it a linear system or a nonlinear system?
Here, output will not be linear with the input. Yt
Output
will
will
not
not.
Yt will not be linear with xt. It will involve differentials and other things.
Output will not be linear with input. Which one?
For a transfer function 1 by s plus 1.
Yes, the first order transfer function. Over there, what you find is, say, for example, if I apply a step input, you would find that there will be transients, but ultimately the system will, it will go to the steady state value. And that steady state value, if you consider, you would find that, I mean, say, for example, if the input is 1 unit, you look at the output in the steady state, right? If the input is 2 units, look at the output. So in that case, you would be expecting that if I say, for example, increase my input 5 times, the output should be increasing 5 times. That is what a linear system would be. I mean, do not confuse the your transient response, which is apparently not a straight line, with the linearity of a system. It's not, I mean, it's not to be confused. Am I
So
clear?
the
What I'm saying is that in the system, there will be a dynamics, right? So you would find that it's going to exponentially rise and go to the steady state value. What would be we be implying by looking at the plot on the left hand side of the board over here is that the output should be doubled if the input is doubled. So say, for example, in the first order, in the case of the first order system, I apply say 1 unit of input, whatever your unit is, right? So I'll get an output, whatever the output is in the steady state, right? So now if I double the input, okay, the output in the steady state should be doubled. Or for that matter, if I half the input, the output in the steady state should be halved. So that is what I would have to look at, not at the response versus time plot, which is going to be confusing me and going to give me a wrong sort of, it's going to lead me in the wrong direction as such.
So
You
this
understand
graph
what I mean?
is in steady state. Input is also steady state. Output is also steady
No,
state.
no. Yes, in the steady state is okay. But what is meant over here is if the input is changed, there should be a proportional change in the output. Yes, of course, in the steady state, that's okay. But if the input is changed, is there a corresponding change in the output? So not, I mean, if you look at that, it's not only in the, if I wish I had the board over here, let me see if I can get some transient calculation. Just a moment, okay, I'll try to, yeah, okay. Say for example, I just need a diagram, that's why I'm, this is for you can see the slide number 66 over here, right?
Yes.
So yes, so
ma'am.
this is for in a different, I mean, sort of for a something which is a different thing. But here on the left hand side, you find a plot which is, can you see my cursor over here, right?
Yeah.
You can see the motion of the cursor, right? So here now I have applied, say, a 1 unit input on the left hand side, this one, and I've got a transient characteristic over here which settles to the steady state value. So now what I mean to say, if this is that if the system is linear, if my input is not 1 units over here but 2 units, then the plot is just going to, I mean, it's going to be, the output is going to be doubled corresponding to that particular input. Or for that matter, if I have this input, say for example, instead of 1 unit input, if I put a half unit input over here, so then again I will see a similar sort of characteristic over here. The transients will still be there, but corresponding to each point there will be a just a scalar reduction of the value only. Do you understand what I'm saying? It's not about only the steady state or the transient part. If the input is changed, the output should proportionately change. So the response in this case, say for example, if I put a 0.5 units of input over here, the response is still going to remain a sort of dynamic response as shown over here. The nature is going to be similar. The only thing is that I will see that the response is going to be, it is going to be for each, I mean, corresponding to each time, a scaling is going to be there. So if I have applied half of the input, the output corresponding to each time is going to be only half. On the other hand, if I were speaking of a nonlinear system, if I halved the input, the nature of my response would altogether change. It is not going to be only a proportional change, a scaling over here, say a halving or a doubling of corresponding to each point or each point in time. I would not be seeing the same or similar response only with the scale factor being, I mean, coming into force. What I would see for a nonlinear system is that it might be that if the nonlinear portion has been reached, the nature of the response is going to change altogether only because the, I mean, the value of the amplitude of my input has changed. Is that okay? In the case of a linear system, the amplitude of my input cannot change the nature of the output of the system. Only a corresponding, I mean, a scaling will be there, and the output to input value corresponding to each point in time would be remaining the same with the scale factor only if I was scaling the your input. If I'm applying, say, half of the input, or I'm applying 5 times of the input or something like that. On the other hand, in a nonlinear system, say for example, if the saturation portion has been reached, then what will happen is that even if I change the input, say for example, I have changed the input 10 times over here, it may be that the output has been saturated at 5 units. So there will not be any response beyond that 5 units. The output will freeze at that particular value, and it's going to be, the characteristic is going to be, the characteristic meaning the plot or response versus time is going to be completely different from what you see over there for a nonlinear system, that is. If it is like
That means output input relationship also changed in case of nonlinear system.
Yes, yes, that is the essence. Output input relation will be changing. That is why you would find that the output to input will not be a straight line as such. Okay,
Okay, okay. Ma'am, a
understood.
simple.
Proportionality.
Okay, okay. Ma'am, a simple resistance is we called a linear system. Yeah.
It's a linear system. It's a static system and a linear
But
system.
RL circuit in case of DC, we can say it is a non-linear. It will be saturated.
RL, no. If it's RL, the response is going to be what you see, somewhat similar to whatever you see over here on my plot. The green response, not the same, of course, but it's going to be somewhat. It's going to have some transients and then go to the steady state value. It's not going to be non-linear. Non-linearity is not going to depend on the response versus time. Rather, what it is going to depend on is that whether if I change the input, the output changes proportionately. Okay. Okay, do not confuse the two, because the plots look similar, especially say for example the right hand side plot that you see over here on this particular slide, the ramp response. It's not, I mean, if you look at the ramp over here, you cannot say whether it's corresponding to a linear system or a non-linear system. It's not possible to say what it is corresponding to. Of course, I mean, it corresponds to a particular if the response is like that, you can say what the dynamics is and all that. That's a different issue. But if I were to see whether it is corresponding to a linear or a non-linear system, I would have to see whether it changes proportionally when I change the input. Otherwise, I will not be able to say whether it is a linear or a non-linear system. So that is why, for understanding whether a system is a linear system or a non-linear system, the characteristic versus, let me bring back that slide. Yes, the characteristic versus time is not to be taken. Rather, change in the input and change in the output is what I have to look at, meaning that the output to input characteristic, where I can actually see whether if I change the input over here, there is a change in the output. Say for example, this saturation characteristic over here, if my input exceeds, say, this x0 or whatever you find over there, anyway, something, some x0 or whatever, so x or something is written anyway. So if the output exceeds this value, what will happen? Now the output is, say for example, corresponding to this dotted line over here. This much is this is the input output line. This is the input that I have applied. So corresponding to that, what is the output? The output will be this much. So this will be the output that I have. Now say I increase the input to a value which is this much. Okay, so this is my input now, input amplitude. So now I find that the output is again the same value as it was corresponding to the previous input. So a change in the input has not changed my output. So that would imply that saturation has been hit, meaning the system is a non-linear system. But mind you, this is the output to input characteristic. So I had to look at what would happen if the input is changed. Will the output change or will it not? So it has actually got nothing to do with the characteristic versus time, the response versus time. Response versus time may be a dynamic one. I mean, you may have transients and then settling. But if the input is changed, whether the response changes proportionately corresponding to each time that you have over there. So all the time ticks, corresponding to all the time ticks, you would have a proportional change in the response if you were looking at a linear system. On the other hand, in a nonlinear system, you would not be expecting, or rather the system would not be having a response which is proportionately changing with time, which makes the system not obey the principles of superposition and homogeneity. By the way, can you people now explicitly define what superposition is? And for that
Yes,
matter, yes, and for that matter, what homogeneity is?
yes.
Right? So those would automatically make us look at what would happen if we change the input. Is there a corresponding change in the output? And how much is that? Following a straight line characteristic as shown over here in the left hand side plot, right? Right. So next we come to again a slide which shows a characteristic, or rather two characteristics for that matter. The left hand side, you find that the output to input has been plotted. Is the characteristic a linear one or a non-linear one? The left hand side one,
Non-linear.
Non-linear.
non-linear, right? Because say for example over here, if I double the input, the output will not be doubled, obviously, right? So here it is, though it is a straight line, it is not a linear characteristic. So I mean it would suffice to say that in case of a linear characteristic, the characteristic should not only be a straight line but also pass through the origin. Otherwise, I mean your principles of superposition and homogeneity would not be holding. Similarly, the one on the right hand side as well. So this one again is a straight line, but it does not pass through the origin. You would find that, I mean, say for example, if I double the input over here, the output is not going to change proportionately, as I mean the characteristic does not pass through the origin, and as a result of that, it is a nonlinear characteristic. Now another classification of systems is whether a system is a continuous system or a discrete system. So over here, basically, a continuous system is a system which has continuity both in the time domain as well as the output domain. So when I say that, let us look at this plot over here, which is shown on the left hand side, where we find that the output is continuous with respect to time, meaning that corresponding to each instant of time, there is an output, right? So here, the time domain is continuous, meaning that I can choose to look at what happens at, say for example, 2 seconds, or for that matter 2.1 seconds, or for that matter 2.1976 seconds. I will get an output value. So the continuity exists in the time domain. On the other hand, in the output domain over here, this is the output domain. So output domain also, I can get, I mean any value is possible. Any value, meaning that when I say any value, I do not mean that all the values should be present in each plot, but what I mean to say is that the output over here is, there are no discretizations over here. When I say that, let us, I mean, compare that with the case, say for example, where the output can either be 1 or 2 or 3, but not 1.1 or 2.3, or for that matter 3.7, right? So in that case, the output domain would have been considered to be discrete, but in this plot over here, both the output domain as well as the time domain are continuous, that is, continuity exists. And so a system which has such a characteristic, such a response, would be considered as a continuous system, or for that matter, continuous systems would have responses which look like this. When I say look like this, of course not the characteristic which is being displayed over here, but what I mean is that continuity exists both in the time as well as the output domain. On the other hand, for discrete systems, basically this discretization may exist both in the time domain or in the output domain, or both, right? So what I mean to say is that, say for example, the characteristic which is shown over here, it is not okay. I had another one.
ম্যাম কন্টিনিউয়াস টাইম সিস্টেমটা আরেকবার বলবেন, যেটা এর আগের বার বললেন ওইটা।
Over here, basically, continuity exists both in the time domain as well as in the output domain. So when I say continuity exists in the time domain, I mean that you can choose to look at what the response value is, say for example at 4.1 seconds, 4.11 seconds, 4.111 seconds, and so on. प्रत्येक time instant there is a corresponding output which you would be able to see, right? What I mean to say is that there would be systems which we'll just come to in a moment, where the output would be visible only at, say for example, 0th second, first second, second and third second, but not between 1 second and 2 second. So is that understood? What I said is that there are systems where the output would be obtained only at discrete instance of time. When I say discrete instance of time, what do I mean? Say for example, you look at this plot over here, the middle one, okay? In the middle one, you find that, let me just zoom in a bit so that, okay, this plot is what I'm trying to show you. Now you find that the dotted lines show you discrete instance of time. Say, let us say this is 1 second, this is 2 second, 3 second, 4 second, and so on. The dotted lines come and join this axis at discrete instance. Now let us say we have a system where there is an impulse at 1 second, an impulse at 2 seconds, different values, but an impulse at the discrete instance of 1 second, 2 second, 3 second, 4 second, etc. But between, say for example, 3 seconds and 4 seconds, this interval, there is no value of the output which is obtained. So in that case, basically discretization has is present along the time domain. You do not obtain the response between the discrete instance where the response is visible. So at, say for example, I repeated only 1 second, 2 second, etc. It may be that it's a multiple of some other value. Say for example, 0.5 is the your sampling interval, that as we call it. So we, say for example, are able to observe the value or get some value of the response at 0.5 seconds, 1 second, 1.5 to 2.53, but not between, say, 2.5 and 3. So 2.7 seconds, I will not be able to get or know what the response value is like. So visualize that you have a set of impulses at those discrete instants only, but nothing in between. So that would qualify as discretization along the time domain, which is what is called a sampled data system. Okay, so sample data system is a system where discretization has occurred along the time domain. There is no response between those intervals. If you were to find out what the response value is between those intervals, there are ways of doing it. Like, for example, I've joined over here. Say, for example, the value, say, at 0 second has been extended up to 1 second, or rather has been held up to 1 second. We use what is called a hold. You will learn that in some other course. And say for example, over here at 0.5 second, the impulse value was this much, but that has been held till the next during that next interval, till the next instant has arrived. So that is possible, but nevertheless the discrete values were obtained for these discrete instants only to start off with, but not between those intervals. So in that case, that system is called a sample data system, but discretization occurs is rather discretization is present along the time domain. On the other hand, there is again another category of systems where the discretization may be along the output domain. What do I mean by output domain? Okay, now in this case, the time domain is continuous, so I will be able to see what happens at 0th second, 0.1, 0.12, etc., etc. So corresponding to each time, I will get an output. But let me say there are, say, only two values or three values which I can get at the output. Say 0, 1 and 2 are the only three outputs that I can get. So let us say that the output can either be a 0 or a 1 or a 2. So in that case, there is no possibility of an output of 1.5 occurring at all. Okay, let me give you an example. You are all familiar with it. I'm formally stating these. That is why it may be a bit difficult to understand in the initial stage. Say, for example, you have a system where the output can either be a 0 or a 1. So you are familiar with that, isn't it? In that case, there is discretization along the output domain. The output can be either 0 or a 1, okay, but not 0.5, etc. Right? So in that case, the output is a discrete one, and discretization exists along the output domain, in which case, what do we call those systems where discretization exists along the output domain?
Discrete time system.
Digital.
All the digital, yes, both sample data systems as well as digital systems are discrete time systems, but in case the output is discrete, those systems are called digital systems. So you see over here in my the tree diagram that you find, basically the all discrete systems can be either categorized on the basis of whether discretization occurs along the time domain, in which case they are classified as sample data systems, or along the output domain, in which case they are categorized as digital systems. So those are both of those are examples of discrete systems. On the other hand, the systems in which both the time as well as the output domain are continuous in nature, like the response I've shown over here, this one would be belonging to a continuous, would be belonging to a this one would be belonging to a continuous time system, in which both the domains, the output domain as well as the time domain, are continuous. So it is possible to get any value for output corresponding to any input, corresponding to any time instant that I choose to observe. Is that okay?
Continuous time and discrete time system is with rest is defined for input only. If we give continuous time input, then we will get continuous time output.
Yes, those things are there. Of course, if you are putting in an impulse, etc., naturally, that is going to give you, that might be giving you a discrete output without any reason. That is not our concern right now. What we mean to say is that the system characteristic itself is such that even if you are applying a continuous input, you would get a discrete set of outputs only. In that case, it is a digital system. And if you are not able to, yes, and also for your for sample data systems, if you are applying a continuous input, say for example I'm applying a step input, but I get as output, I get a series or sequence of pulses only, right? So in that case, that would be considered as a sample data system. Okay.
Okay.
Ma'am, someone wants to join. Can you please allow him?
Okay,
his
let
name?
me see. Yes.
Sample data system is discrete in time, but it may be continuous in
Yes.
output.
Yes.
Okay.
Yes. Output will be continuous, will be in general continuous, okay. What is of interest over there in sample data systems is that the output will not be, obtainable, say between, say for example, if you have a very simple example would be a case of, say if you have in an electrical system a switch which is closing at the 0th second, first second, second, third second, right? So the output will be there at all only at those discrete instants, and elsewhere you will not be able to get the value of the output at all, right? Because the switch is open in the first case. So so that would be classified under the category of sample data systems. So even if I put a continuous input over there, the output I will get only at those discrete, say tth second and 2t seconds, 3t second, and all that, where t is the sampling time. Okay, so basically here this the same diagrams have been sort of zoomed on to the left hand side. I think I have sufficiently explained. Only over here, I mean, the sequence of pulses has not been shown. I usually use the blackboard to draw it, but unfortunately this year I have to just verbally say that. I hope you have understood what I meant by a sequence of pulses only being the output, and the diagram response that is shown over here is a response for a sample data system with what we call a 0th order hold. You will be learning all those if you have not done yet. I think you have already, haven't you? 0th order hold in your measurements somewhere. You must have uh, done it, or you would be learning that in any case. So here, what I mean by 0th order hold is that, I mean, I'm not going to go into the details of the 0th order hold. What I mean to say is that the previous value is held constant at the, I mean, till the time the next output occurs, that is the next instant where you get a different value for the pulse, where the pulse value changes, and then again it is held constant for the remaining interval. So this, I mean, after the 0th order hold has been applied, of course, the output is continuous. So, I mean, though it was for a sample data system, the diagram that has been shown over here corresponds to an, I mean, a sample data system where a hold has been used, where you find that now I do have outputs in the intermediate intervals. So this would no longer, I mean, qualify as a sample data system, rather a sample data system with a hold is what we call it. But anyway, that's beyond the purview of this. Just keep that much in mind. That is for the time being, and let's proceed. On the other hand, the right hand side diagram again, we are not going to go into the details of this. What you find over here is that, say for example, there are two states in this particular system, pump on and off, like the 0 and 1 that we spoke of and so on, right? So say pump on and pump off are the two states. Maybe there is a pause state, so three states over here. So the pump can either be on or off or in the pause state. No other possibility exists. So once, I mean, it has been started until the pump has been stopped, I mean, we are no longer considering it for that matter, there can be three possible states only. So that could be categorized under, I mean, discrete systems where you have the output having one of several states, as we call it. So it is going to belong to the category. The particular example that I've shown over here actually is called a discrete event system, but nevertheless, I mean, digital systems would be similar if you look at them, either a 0 or a 1, but nothing in between are the possibilities. So in any case, that is not a continuous system, it is a discrete system. So now coming to the next category, which classifies any system into either a time invariant system or a time varying system. So now again, you find that the system, say for example, if I have a pure resistance, or for that matter a resistance RL circuit like the one that I'm pointing to right now, if you can see my cursor. So the dynamics of the system is described by this equation Vt, V as a function of t, that is equal to It to R plus L dit dt. So that actually describes the dynamics of the system. Now can you tell me whether this would be considered as a time varying or a time invariant system? Now, before I ask you that question, let me tell you that in a time invariant system, the parameters of the system would remain constant over time, that you see written on the left hand side. Whereas in a time varying system, the parameters of the system would vary with time. So basically now my question, coming back to the question, this one, that is V equal to IR plus L di dt. Is this an example of a time invariant system or a time varying system, and why? Can you try to answer that?
Ma'am,
Invariant.
time invariant because here R and L are constant parameters.
Yes. So that is something which you need to understand very well. that is, R and L are the parameters of this system, not the current, not the voltage, mind you. Okay, those are not the parameters of the system. Those are the variables of interest, fine. They are going to be going to vary with time. That is the current and the voltage automatically will be varying with time if we are dealing with a dynamic system. Any dynamic system will have transient and steady state, etc. But the current is going to be a function of time, as will be the voltage. In general. But the parameters of the system, namely for this system, the resistance and the inductance, are not dependent on time. They are constant. So in this case, the system is the system which has been described by this mathematical expression is a time invariant system. On the other hand, this system, that is the equation that you see over here, that is Vt is equal to It Rt plus Lt dit dt. So over here, apart from the variables being functions of time, that is I is a function of time as well as V, you find that in this case the parameters, namely the resistance as well as the inductance, are also functions of time, which means that the parameters are time varying, and hence the system itself is time varying. So basically this is an example of a time varying system because the parameters, namely R and L, are varying with time, right? So whenever you again encounter a system, do not confuse the parameters with the variables. First of all, identify which the variables are and what the parameters are. Then have a look at the parameters. Are those parameters functions of time or are they constant? If the parameters are functions of time, only then the system is to be considered as a time varying system. On the other hand, if the parameters are constant, then the system, irrespective of the fact that it is a differential equation, and for that matter current and voltage are also functions of time, etc., etc., since the parameters themselves are constant, the system is a time invariant system. So say for example, if I have a static system where there is a pure resistance, but the resistance is actually sorry, a function of time. So V equal to IR, but Vt equal to It Rt, say for example, R also is a function of time. That would be a time varying system. Though it is a static system, but nevertheless, you would find that that system is a time varying system because the parameter, namely R in that case, is a function of time. Next, we come to another categorization, which is known as lumped parameter or distributed parameter control systems. So on the left hand side, you find a pure, circuit where a pure resistor is present. You find a DC power source and current flowing, etc. Here, basically, the parameters are lumped. On the other hand, you people are, familiar with the system that or something similar to that I've drawn on the right hand side, which describes, or which denotes power distribution lines where the resistance or the inductance or the capacitance cannot be considered as to be concentrated at particular points, either in space as such, but they have to be considered as distributed parameters. So in that case, such systems would fall under the category of distributed parameter control systems. On the other hand, the left hand side where the parameters are lumped are considered as lumped parameter control systems. So that is all regarding the categorization of control systems based on some property or aspect of it, right? So now we are going to go into the next module, which is that actually sort of brings us to the end of the introduction part as such. Now we are going to go to the steady state error and error constant analysis or study, right? So Let me just have some water. So right now we are going to start with after the introduction, we are going to start with the next thing which we have in our course, that is study of steady state errors and error constants. But before going to that, what we are going to do is we are going to study the different inputs which are present in the or rather which are applied to systems in order to check whether or in order to see the errors, the steady state errors, and study them. I'll just go to the description of the inputs first, come back to those slides in a moment. So there are three standard inputs which are used for error analysis, that is study of steady state errors and error constants, which are the step input, the ramp input, and the parabolic input. So the inputs are shown over here. I hope you can see the slide number, what is it, 67, right?
Yes, ma'am.
So yes, so you see that there are three standard inputs which are shown over here, and in these, basically these are actually applied in order to do analysis of the errors in the system, and for that matter steady state errors. Now there's a question which has been, in fact two questions that have been put up over there, one of, I mean each of which we are going to just sort of contemplate on before we go to anything else. The first question over there you see is, which amongst this is the most severe? So now this question is sort of a bit, you can say it's vague, you can say sort of in the, it's sort of, you can say it's not very, what should I say, in layman's language actually, it can be framed in that fashion, that is, which is the most severe. So when I say severe, what I mean is that given a choice, which of these would I want to apply if I were to test a system? So let me reframe that or repeat that. What I mean to say is that if I were given a choice and somebody tells me, okay, you can opt for only one sort of input and see which whether your system is acting properly, or rather acting satisfactorily for that matter, which of these would you choose? So naturally, the, I mean, thing that would come to your mind is that I would have to test my system and see whether it is satisfactory. So in order to do that, the best way of doing that would be to see whether my system is responding in the satisfactory fashion given the worst possible input that I can give it, right? So when I say worst possible, what would I mean? Say if I would normally mean that the system would be pushed to its limits, or for that matter, I mean, I mean, that would be the worst possible input which I can give to the system, and all other inputs that I would be able to put would be better than that particular input. So if that were the case, which of these inputs would I be choosing? Would it be the step input or the ramp input or the parabolic input? You can see the three drawn over here, sketched over here, and you're familiar with those also for, I mean, from your study of signals and systems, I believe. So now, as far as the severity is constant, which of these do you think would be the most severe and why?
Ma'am, RAM, because with increasing T, it is going, RT also increasing, so it may be infinity once.
Okay, that is one answer. Anybody else with any other answer and why? No one else with any other possible answer? All of you agree with him. That is, the ramp is the worst possible input because the input is changing with time, so called. Anybody who does not agree with that?
Ma'am, I think it will be parabolic input because the input is changing with square of time. So if
Okay.
I mean with
Okay.
increasing time, the input will keep on increasing, and so
Yes,
the
ma'am.
signals
Output will be more affected.
yes, yes. So we won't be able to reach any steady state for that.
Yes, it's right.
Okay. Anybody who thinks both of them are wrong? See, I'm giving you such a lot of, so much of freedom, so called. Anybody who thinks the step input would be worse than the others?
Ma'am, step input means only one root at origin with multiplicity 1. So
Mhm.
it can be stable, but ramp and parabolic correspond to 1 by s square and 1 by s cube. So they might be even more severe because they don't have that kind of stability.
You are speaking of mathematics, but I am speaking of, say, okay, thank you for expressing your views. Now, let us say that say, for example, if you are standing somewhere, right? Sort of, I'm assuming that nobody else has a different answer compared to what you or three or four of you told me. So let us say somebody is standing somewhere, right? And there's another person who is going to sort of try to move him by applying a force, right? So would, say for example, person X is standing somewhere and person Y has to apply that force. Now, for getting the best possible results, would the person Y choose to give an instantaneously large force and apply it over there, or choose to increase the force little by little and keep on increasing it with time, or to use a square law, meaning give a very small force first and then keep on increasing it, and then it's going to keep on increasing. Which one would produce the best possible effect? Best possible meaning that you want to displace that person, make him fall down, say for example. Which one would you,
Instantaneous.
isn't it so? So instantaneous, input applied at a particular instant is effectively going to be the worst possible input that you would be able to apply, compared to the case where you are increasing bit by bit, say for example in the ramp, or for that matter in the parabola, where the start is very less, right? In the beginning the uh, force or input, is very less, and gradually you are increasing. So in case of a step input, there is an instantaneous change from one previous level of input to a different level of input at a particular instant. And then this value that you see constant over here means that physically, if I want to see what with respect to those two people, one who was standing over there and the other who was trying to displace him, what would correspond to a application of a step input? First of all, at a particular instant he's going to go and give a very big push and then keep on pushing with the same force henceforth, meaning for all subsequent instance, again the same force is going to be applied. So basically, application, the step input that you see, as apparently see as a remaining constant over time, is physically not, physically amounts to application of keeping the input applied even after that initial instant where you changed it instantaneously, right? So that was what a step input is. And for, if you agree with what I said, basically that is the reason why a step input is often preferred over a ramp input, or for that matter a parabolic input, if you were to see the worst possible response that you want from the system. So that is why you would see that even in your signals and systems, and in fact in this course as well as if you, I mean, have other courses in control later on, process instrumentation and control and so on, you would be finding that, I mean, most systems you would be actually looking at the step responses. It's not because step responses are easy and the teachers are trying to, I mean, get away with doing something easy. It's not actually that. It is because the step input is a conscious choice to see whether or what sort of effect an application of an instantaneous input on the system and then keeping the input at the same value would be how it would be affecting the response of the system, compared to the case where you are choosing to or opting to increase the input gradually in both the others, I mean, namely the ramp and the parabolic input. Now the next question, that is the impulse input more severe than these inputs? So let us say, okay, I forget about the infinite impulse, which is difficult to visualize. Let me say I have an impulse of a large but say finite value. Is that better than or worse than the three inputs that you see over here? Now,
More severe,
why more severe?
because at the instantaneous only we are applying so large value to the system, so it will have to incorporate so many changes of that large value.
Fine, but yes, large value, but so is the case in the case of a step, isn't it? You are assuming an infinite value or a very large value, that's a different issue. But if you are speaking of applying an instantaneous input at a particular, I mean, of a finite but large value at a particular instant, that is, it is the same for, I mean, as far as a step is concerned, in the step also you have an instantaneous application of a particular input, isn't it? So why
Uh,
not, I mean, which is I mean,
its
hmm?
frequency response will contain all the frequencies, so we'll be testing the system for all the frequencies.
That is okay. Testing the system for all frequencies is okay, but the question is, I mean, whether this is more severe compared to that. Severe, by severity I mean that, say in this case of an impulse input, what would we be doing? We would be applying, again consider the case of those two people that I was explaining, person X who is standing and person Y who is applying. Say for example, at a particular instant he is applying a very big force to the person, I mean a very big force on the person. But in the case of an impulse, what is he doing at the next instant? He is withdrawing that force, isn't it? In the
Yeah.
case of an impulse, instantaneous application and then withdrawal of that force. On the other hand, in case of a step, the instantaneous application of that force is going to be there, but the same constant value of the force is, hence, I mean, after that instant, it's still going to be applied on that uh, person in that case, and let us say. So, I mean, in the case of a step, the input is not withdrawn, right? The input is still being applied at subsequent instants. So in that case, I mean, what I am trying to drive at is that the step input is a sort of natural choice for observing what the response is going to be like. Of course, if I want, I mean, specific sorts of responses, or I mean, I'm going to use, or rather do an analysis with a specific purpose in mind, that's a different issue altogether. But in general, step inputs are the most preferable of all inputs, not even the impulse input, right? Why not the impulse input? Because after the initial instant, the impulse input actually amounts to withdrawing the input value, meaning that you are applying, I mean, an instant, at an instant you're applying a particular input, but then withdrawing it instantaneously. On the other hand, in the step input, you are keeping the input being, the input is still being applied at subsequent intervals. It's not changing, it's not increasing further, or is it decreasing, but after the initial application, it is kept at the constant value. It's still being applied to the system. So that is, I mean, a bit of a discussion, which is, I mean, purely you can say qualitative in nature as far as what I have done. Mathematically, of course, you would be having to see the responses and all that and see whether which one is qualifying for your case. But nevertheless, what we have qualitatively stated over here would still be seen to be valid. Meaning, if you have done the step response, seen the step response and done your analysis, it would mostly serve your purpose, and you would be able to design the system based on that. In most cases, most meaning for specific cases, we will come to many such cases as we go by, where different, say for example, the ramp response is what you have to see, otherwise it's not going to be sort of, it's going to become trivial. So in that, I mean, in those specific cases, it's a bit different. But apart from that, the step input is the one which is normally preferred as, I mean, a signal which is to be applied for the analysis of systems. Now, let me, I miss my board work now, but let me just try to, okay, I think this is the slide I should be showing first. Okay, so now we will go to the analysis of steady state errors in systems. So for that, we would be doing the analysis by using the three standard inputs that we just discussed, namely the step, the ramp, and the parabolic inputs. But before going into that analysis, we are going to see something which is known as, first of all, the error transfer function, and hence the steady state error. So I hope you can see the slide number 71, which is being displayed over here. In the diagram, you find a block diagram over there with a forward path transfer function GS and a unity negative feedback. And an input RS which is being applied, the output is CS. Fine. So here now the closed loop transfer function, as we already discussed in the first class, many of you were able to actually tell me what the closed loop transfer function is. So CS by R will be given by GS by 1 plus GS, because it is a unity feedback system, HS is equal to 1. Now, if we want what is known as the error transfer function, which is defined as ES by RS, that would be given as 1 by 1 plus GS, right? So ES by RS would be given by 1 plus GS. Now, since I'm just verbally stating these, if you are unable to understand, please tell me. I'll try to use some word file or something and try to write down things, because deriving on the board is one thing and just verbally stating is a different thing. I cannot understand, nor can I see your faces. So I will not be able to understand if you are unable to follow. So please tell me immediately. ES by RS is the error transfer function and is given by 1 by 1 plus GS. It can be derived from this directly. That also you would, I mean, be knowing. Now, the steady state error is defined as the error as time tends to infinity. So, ESS is the notation which is used for steady state error and is defined as the limit of ET as t tends to infinity. ET being the error as a function of time, and as t tends to infinity, the error would be equaling or reaching the steady state value denoted by E suffix SS. So if I were to calculate, if we were to calculate the ESS, that is the steady state error, by finding out what the error value is going to be as t tends to infinity, we apply what is applied over here. You can see something has been applied. What is the theorem that has been applied?
Final.
Yes, the final value theorem is applied such that limit of ET as t tends to infinity can be calculated from limit of SES as s tends to 0. So now ES would be, if you recollect, we had found out the error transfer function ES by RS as 1 by 1 plus GS. So ES will be equal to RS by 1 plus GS. So that is replaced over here, and we find that ESS will be equal to limit of SRS by 1 plus GS as S tends to 0. So this is the expression for the steady state error. If I were to if I were to find out the steady state error, I would have to do it from this expression, that is ESS is equal to limit of SRS by 1 plus GS as S tends to 0. Of course, over here you would notice two things. One is that the steady state error is dependent on the RS, that is the input to the system. Also, the steady state error is dependent on GS, which is the transfer function of the system. And for that matter, the forward path transfer function. If I was speaking of only a unity feedback system, the forward path transfer function is what the steady state error depends on. So I repeat that the steady state error of a system depends on the input, that is RS, as well as the forward path transfer function GS, right? So now, given a particular input, the steady state error can be appropriately derived by using this expression. For example, if I have applied a step input to my system, RS would have to be replaced by the amplitude
1 by
value
S.
by S, yes, 1 by S into the amplitude value, and then I would have to see what my steady state error is. Similarly for other inputs, so it can be derived from this expression itself. So that is what we are going to do right now in order to derive the steady state errors corresponding to different inputs. So I actually go back to we go back to the case where a unit step input is being applied to the system. I hope you can see this slide, which is slide number 68, right? So the input in this case is a step input. So you can see over there within bracket, it's written position command. So where does this position command come from? You would recollect that in the last class I had stated that servo mechanisms were basically the systems which were initially considered as the only control systems, for that matter, which were in use. So all those, terminology have, at least, for this set of the steady state and error analysis, the terminology has been derived from the servo mechanism terminology. So, a step input would be a position command, ramp input would be a velocity command, and parabolic input would be an acceleration command, and so on. Right. So basically, because these come from this servo mechanism terminology, that is why this term is being used for a step input. You would find it in many books. That's why I've put it over there. But nevertheless, right now we are going to see what happens when a step input is applied to a system. And for that matter, a step input of unit amplitude. So we call it a unit step input. In that case, if my input is some UT and the input amplitude is unity, then RS will be equal to 1 by S. So in that case, coming back to the expression that I showed you just some time back in the previous slide, not previous with respect to this, slide show over here, but the one that I just showed you before this one. The steady state error would be directly obtained as ESS is equal to limit of SES as S tends to 0, and for that matter, limit of S tends to 0, S into RS by 1 plus GS. So RS in this case is 1 by S, which we have substituted over here, and this is what we come to. So over here, obviously you can see the S cancels out, and we are left with limit of S tends to 0, 1 by 1 plus GS. So this would be giving us the steady state error given a unit step input. So now this can be written as, you find that in this we have to calculate the limit as S tends to 0 of 1 by 1 plus GS. Now in these, 1 in the numerator as well as denominator will remain as it is, as S tends to 0, no change over there. The only term which contains S is the GS over here. So if we define the limit of GS as S tends to 0 by G0, that's actually written over here in the next, just below that. So we are for the time being substituting G0 as the notation to denote limit of GS as S tends to 0. So we can rewrite this, that is ESS is equal to 1 by 1 plus G0, where G0 is nothing but the limit of GS as S tends to 0. And then again another notation is used, which is K suffix P, P standing for denoting the position error constant. Again, the word position comes from the servo mechanism terminology, but Kp actually denotes the limit of GS as S tends to 0. So if we are given a system, and for that matter, the forward path transfer function of the system with a unity negative feedback, we have to, and somebody tells you, okay, a unit step input has been applied and you have to analyze what the steady state error is. What you would have to do is you would have to find out the value of the position error constant, which is denoted by Kp, which is given by limit of GS as S tends to 0. And then in order to find out the steady state error, once Kp has been found out, you can calculate steady state error by calculating this, that is 1 by 1 plus Kp is going to give you the ESS. So if we are speaking of the application of a unit step input and you have to calculate the steady state error, the first thing that has to be done is calculation of the position error constant, and then calculation of the steady state error by putting it in 1 by 1 plus Kp. That is going to give you the value of the steady state error in case of a position command or the step command. Next, we come to ramp input, and for that matter, ramp input of unit amplitude, which we call a unit ramp input. And again, that is called a velocity input, going by the same, same arguments that we spoke of. Not arguments actually, because the terminology has come from the servo mechanism terminology, that is why it has been, it is used actually. So velocity input means nothing but the ramp input. So now again, if we were to calculate and find out the steady state error in this case, so input Rs is equal to 1 by S square, because it is of unit amplitude, and a ramp, that is 1 by S square. So the ESS is again limit of SES as S tends to 0, where we have limit of S into RS by 1 plus GS. So now in this case, if you recollect what we had done on that slide number, I think 71 or something. So now RS is replaced by 1 by S square, and one of those S's cancel out, whereas the other remains. So we are left with limit of S tends to 0, 1 by S plus SGS. Now, if you look at that expression, you have to take the limit as S tends to 0. So what is the limit of S as S tends to 0? What is the limit of S as S tends to 0?
0.
Only 0. So that actually vanishes when we take the limit. So we are left with 1 by 1 by limit of SGS as S tends to 0. So basically that S has vanished, and we are able to rewrite that as limit as S tends to 0 of 1 by SGS. And now again in the numerator, that's a constant, so the limit is going to be taken only on the denominator, and that denominator has been, after taking the limit, that is, has been replaced by a notation which is K suffix V, which denotes the velocity error constant, and is calculated from the limit of SGS as S tends to 0. So Kv, that is the velocity error constant, is calculated from limit SGS as S tends to 0. And if you were to calculate the steady state error in case of application of a ramp input, the first step that you would have to follow is that you have to calculate the velocity error constant Kv by putting this, that is limit of S tends to 0. Once Kv is calculated, the steady state error, that is ESS, will be equal to 1 by Kv only. So that will actually give you the steady state error in case of a ramp input. Similarly, for a parabolic input, again, parabolic input is what we consider, and Rs is equal to 1 by S cube, and ESS will be equal to, again, limit of S RS by 1 plus GS, which is S by 1 plus GS into, if that is the case, now we are left with this, that is ESS is equal to limit of 1 by S square plus S square GS as S tends to 0. So over here again, S square as S tends to 0 is going to be equal to 0, and we are left with limit of 1 by S square GS as S tends to 0. So that again, brings us to 1 by the denominator with the limit being taken, that is limit of S square GS as S tends to 0, which is replaced by the notation K suffix A, which denotes the acceleration error constant. So Ka is the acceleration error constant, which has to be calculated using this, that is limit of S square GS as S tends to 0. And once Ka has been calculated, the steady state error can be calculated simply from 1 by K suffix A. So given a unit parabolic input, if you were to find the steady state error, you have to find out 1 by Ka. So for that, first the acceleration error constant has to be calculated based on this relation over here, and then 1 by Ka would give you the steady state error. So this is how the steady state errors are calculated and the error constants get their names. Now I will actually go back to the first slide that I actually skipped, first meaning the first slide after this. So now coming back to steady state error and error constants, why at all we need to find out the steady state error and the error constants. So the steady state error is a measure of the system accuracy, meaning that if I apply a step input, whether my output will follow the step. If I apply a ramp input, whether my output would follow a ramp. So whether or how closely the output would follow the input signal is what I mean by observing or finding out the steady state errors. Note one thing, that is basically in the figures that are shown on this page, I have used a step and a ramp. So in the case of the ramp, though the input is changing and hence the output is also going to be changing, nevertheless we do speak of steady state error. So what does a steady state error over there in that case imply? It implies that there is a constant difference. Say for example, if I have a constant steady state error of 0.5 units, what does that imply? It means that after the transients are over, if I have applied a ramp, the error or the difference with the input of the output would be that 0.5 units or whatever the steady state error is. And that even if the input is, following the ramp and it's keeping on increasing, the output also would keep on increasing, by following the ramp, but that constant difference with the input would still be remaining. So that is, implying the steady state error. So somebody may argue, ma'am, here the steady state is not reached at all. No, what I mean over here is that it is the difference with the input which has been applied. So if that difference with the input is constant, I say a constant steady state error is what is present, right? So what I showed to you just earlier would give you some values, etc. The physical interpretation has to be done for the specific inputs by keeping these things in mind rather. So a constant steady state error in case of a ramp input would amount to the output following the ramp, but with a specific difference which is equal to that error that you have calculated. Now this error, meaning the steady state error, arises from, this we've just discussed, the nature of the inputs and the type of the system. Type of the system meaning that what we have stated till so far is it depends on the forward path transfer function GS, right? So what type of the system means we'll come to in a moment, but before that, basically, it would suffice to say that the error would be arising from the forward path transfer function of the system. Depending on what the system transfer function is, it would be, the error would be calculated. It would be dependent on GS. And from non-linearities of those system components such as static friction, backlash, etc. So if there are non-linearities, of course, the error would be affected by those non-linearities. but we have not done any study on nonlinear systems. Naturally, we are, I mean, here to study linear systems, at least as a starting point. So it would suffice to know that if you have nonlinearities, the error would be not, I mean, it would be different from what you have calculated and what you have analyzed. The steady state performance is usually judged by a steady state error due to the standard inputs, that is the step, ramp, and parabolic inputs. Now, steady state performance can also be, I mean, judged on the basis of other inputs as well. But nevertheless, as far as the three standard inputs are concerned, basically steady state error analysis is normally done by using these three standard inputs only. These, I mean, inputs are applied and the performance is analyzed. But nevertheless, I mean, what I meant to say is that a similar analysis can be done even for, I mean, inputs which do not belong to these three inputs only. Similar analysis can be done, but as far as the analysis by using error constants is concerned, it depends on, I mean, it makes use of only the three standard inputs. Recollect that we have spoken of a unit step input, unit ramp input, and unit parabolic input, in which cases they are called the position input, position command, or velocity command, or acceleration command. So these are the standard inputs which are used, but similar analysis can be done for other inputs as well. The concepts of steady state errors and error constants is valid only for stable systems. So this thing is very important. For unstable systems, I mean, there's no question of steady state, in fact, and for that matter, steady state errors. Even if you calculate something, that is going to be wrong or not relevant, at least you can say. So, if you are going in for an error analysis, the first thing that you have to look at is whether the system is stable in the first place. Only then the steady state errors and error constants can be calculated or need to be calculated in the first place. So yes, over here the steady state error has been shown. I mean, physical, what it means has been shown over here in the two diagrams. And on the left hand side diagram, you find a step input has been applied, and here the response is the green one that you see. There is a, I mean, after steady state is reached, there is a constant difference with the input. You find, say, for example, after 9 seconds or so, you would be seeing that there would be no further change in the output, and the difference of the output with the input that exists is going to be termed as the steady state error. On the other hand, in the case of a ramp input, also, you could be calculating the steady state error. Here again, you find a transient portion. So in general, you would find, I mean, you would expect rather that if I apply a ramp input, the output should be following a ramp. But naturally, because of the dynamics of the system, there are transients which are present, which you find over here, say up to about 8 seconds or so in this particular case. And then you find that after that, there is a constant gap between the input and the output. So that gap, so-called, is basically the steady state error. It is the difference of the output with the input, and is, I mean, in this case, for a constant steady state error, it is going to remain constant. If the steady state error is going to be, I mean, varying, etc., then we will see, I mean, how that is interpreted and how those diagrams are going to look like. I think we do have, I mean, chart where such diagrams are present. But this case particularly demonstrates a constant steady state error in case of a ramp input, how it is going to look like. So these slides I've already used to explain certain things. Now we encountered a term which is known as the type of a system. So over there I just told you, okay, you need to know the limit of GS as s tends to 0 or limit of SGS as s tends to 0, etc. So GS, it's going to be dependent, the steady state errors are going to be dependent on GS. Here we get a bit more specific and we say that the steady state errors would be depending on what we call the type of the system. But before, going to the steady state errors and how they are dependent on the type of the system, we'll see what the word type means with respect to a feedback control system. So if the open loop transfer function, if we are considering the open loop transfer function of a unity feedback control system, it can be written in two standard forms. I believe you are already familiar with these two forms. The time constant form, which is the form where you have 1 plus s tau form for all the poles and the zeros, and the pole zero form where you have the s plus z or the s plus p form for the numerator and zeros and poles specifically. So each and every system, any system for that matter, can be expressed in either of these two forms. Of course, linear systems is what we are speaking of, where the transfer function is of interest. They can be expressed either in the time constant form or in the pole zero form. Each system can be, it's interconvertible. You can express it either in the time constant form or convert it into the pole zero form as per your requirement. In both these forms, you find that, first of all, there are several things that you have to keep in mind. The first thing is that, of course, the numerator order will be essentially lesser than or equal to the denominator overall order. I hope you are familiar with that. That is something that has been given over here mathematically. That is, m is lesser than or equal to small n plus capital N, where capital N is the power of the single s term, and you have the others, other poles that are present over here. There are a small n number of other poles present. So the numerator order should essentially be lesser than or equal to the denominator order for all physical systems, right? So you would be familiar with that from your knowledge of signals and systems. Otherwise, it is not a physically realizable system, or for that matter, a practical system. So that is something to be kept in mind. Now, apart from that, you just look at the time constant form over here. You find that there are certain zeros and certain poles, and there is an s to the power of capital N over here. So what does this is 1 by s to the power of n as far as the transfer function is concerned, has been multiplied with the rest of the terms. So what is 1 by s? What does it indicate? What does it physically indicate? 1 by s? What action does it indicate?
Poles at the origin.
Yes, poles at the origin, of course. But physically, what does it denote? Denote meaning what sort of action is, how does 1 by s come in the first place? If you have a system, when will the 1 by s be there?
Integration.
Very good, yes. So there is an integration present. One integration would amount to 1 by s, double integration 1 by s square, and so on. So s to the power of n, that capital N over here, actually denotes the number of integrators which are present in the system, right? And basically, the term, yes, s to the power of n in the denominator corresponds to the number of integrators in the system. And basically, this capital N is what we call the type of the system. We'll actually come to that in a moment. Now, type of the system, why type of the system? Because we will see that in error analysis, the number of integrators is of great interest to us, in the sense it is of importance as far as the calculation of the error constants and steady state errors are concerned. So that is why that importance has been given to the number of integrators present in the system, and we call the system as type 0, type 1, or type 2 based on the number of integrators which are present in the system. So say, for example, if we do not have any integrators, say for example, if you have a first order system k by s plus 1, so how many integrators over there? There are no integrators. That would be called a type 0 system, because there are 0 integrators. Similarly, a system where you have the 1 by s present, that would be a type 1 system. You would be having a type 2, type 3, etc. systems, depending on the number of integrators which are present in the system. Now, why the number of integrators are all that important, we'll just come to, and you would understand that. So before we go to that, yes, so type basically indicates, it's going to give you a feel of the actual nature of the system. It's going to tell you how it is going to act. So that is why the name type has been given to the type 0, type 1, and type 2. Now, what I stated is put over here in the slide. So the type of the system could be type 0 system, where capital N, that is the number of integrators, or s to the power of capital N, is what we have over here. The capital N is equal to 0 means it is a type 0 system. Capital N is equal to 1 means it's a type 1 system. N equal to 2 is a type 2 system. You would
Ma'am,
also find, yes.
why we are taking the open loop transfer function? Why don't the closed loop transfer
We'll
function?
come to that. We'll come to that, because in error analysis, GS is all that going to be. We will find that GS will be the important thing to be considered. So that is why we are interested over here. Of course, we are speaking of only the terminology, but why it is of interest, we'll be coming in a moment. We'll see that in error analysis, the open loop transfer function is the all important thing, irrespective of, whatever else happens, right? So here, the terminal, as far as the terminology is concerned, we could also encounter in some books a type -1 system, where actually it means that a differentiator is present, meaning an s is present in the numerator. But anyway, n equal to 0, 1, 2, etc. The type 0, type 1, type 2, etc. systems are defined in this fashion depending on the number of integrators. Now, yes. So now you would actually, recollect that we had already seen this slide, that is ESS, that is a steady state error in case of a position or step command is calculated as 1 by 1 plus Kp, where Kp is limit of GS as S tends to 0. So now if, say, we were to find out the steady state error due to a step command, what would we do? The steps involved would be as follows. We would first calculate the position error constant by using this expression, and then we would substitute it in the expression for ESS, which is equal to 1 by 1 plus Kp, and that would give us our steady state error value. So now if we were to calculate the steady state error, we would have to to a step command, that is, we would have to calculate Kp. In order to calculate Kp, it is essential to calculate this, that is limit of GS as S tends to 0. Now just look at this. You want to now look at only GS, that is the forward path transfer function only, not the rest of it, right? So that actually partially answers your question. We will appreciate more of this as we go by. Limit of GS as S tends to 0 is what we are interested in. So if we are able to find that, we will be able to find Kp, and hence we would be able to find out ESS. Now imagine a case where you have a type 0 system, right? So a type 0 system would, say for example, if I say K by S plus 1, okay, so that is my GS. GS is equal to K by S plus 1. It is a type 0 system, right? Should I write it somewhere? And can you understand what I'm saying? What I'm saying is, I'm considering a type 0 system, a simple example of a type 0 system, okay? So now, can you calculate the value of the Kp for that?
K, a
That
constant.
will be equal to constant K. So constant K is what we would be getting. So if we were to calculate the steady state error, that would be 1 by 1 plus K.
Finite
So
constant.
yes, finite steady state error is what we have landed up with for a type 0 system that we have taken specifically in this case. Now let us consider that was a, first order type 0 system. Let us consider a case where you have a single gain K, that is your static system, and you have just K as your system. So what will be your what will be your position error constant in that case? Again, it will be limit of K as S tends to 0, which is going to be equal to K. So ESS will again be 1 by 1 plus K, which is going to be a constant, finite constant value, right? Fine till so far. Now let us consider a second order type 0 system. So one example could be, say, second order, but type 0. How could, I mean, you, what could you write? I mean, can you give me an example of such a system?
1 by a square
I'll,
plus 1.
K by a square. Is
A square plus
uh,
2s plus 1 a by.
exactly. So if there are no 1 by ss standing alone, you can have, say, for example, k by s square plus as plus b or something like that. Okay, so whatever. So in that case, now that is again a type 0 system. So k by, let us say, s square plus uh, okay, let us say k by s square plus s plus 1, to simplify matters a bit, just to simplify. Okay, so k by s square plus s plus 1 is what our system is. It is a type 0 system again, but a second order type 0 system for that matter. So what is the kp value in that case?
K, K constant K.
Again k. So ess will be now again equal to 1 by 1 plus k, which is going to be again a finite constant. So we would be finding that in that example, of course, I mean, you could be changing the values of the constants, the parameters over there, say s square plus as plus b, etc., etc. But even if you do that, what will happen to the position error constant? The constant value will be different, but it will be a constant, right? So kp, position error constant, in case of a type 0 system, will essentially be a constant, whether it is a first order system of type 0, second order system of type 0, third order system of type 0, etc. So a type 0 system will yield a constant steady state error, is what we can say. It is, I mean, the basic thing that we can claim is that a type 0 system will essentially, if a position command is applied, of course, will essentially yield a steady state error which is constant, right? Similarly now,
Ma'am,
yes.
suppose the open loop transfer function is given, and we have to find the ESS. First, we have to find system is stable or not, isn't it?
Mm-hmm. No,
For
you have
that,
to find whether the system is stable means obvious. Yes, unstable. Obviously, unstable systems would be
there's
I
no
mean,
value for the ESS.
yes, then there's no value for the ess, of course. Yes, over here we are not for this analysis, you are correct, we have omitted the, I mean, stability analysis over here. That itself would I mean, involve a lot of different issue, a lot of things to study. You are going to do that in the next part. But if you, I mean, find that the steady, you are, I mean, finding some error constant and the steady state error, and it is not making sense, then please be, I mean, sort of careful and try to find out whether the system was stable in the first place. That is the least you can do, at least for the time being, right?
Ma'am,
Because
for that
if
case,
you
we have to calculate first the CLT.
no, yes, for steady state, I mean, for error analysis, sorry, for stability analysis, whatever you have to do, you have to do. That's a different issue. But for, I mean, systems where you are interested in the steady state error only, you can, I mean, say for example, I'm speaking of a first order system where I am speaking of only the first order system, which is a type 0 system. So over there, if I just look at the pole placement, whether they are in the right or left, I would be able to see whether the it is a your stable or not. Open loop stability, of course, I'm speaking of right now. Okay. Closed loop stability, of course, if you have to find out, you would have to find go into your methods of analysis, etc. We are not going to go into the complications of stability analysis right at the moment. Rather, we are going to concentrate on, we are going to assume that given stable systems, and if we are to calculate steady state error, we would have to use the methods that we are outlining. That is the least we can say right now. Okay, what we are saying is that, say for example, if you are speaking of an unstable system, the response itself you would be finding is going to be divergent, and it is going to become very large. So I mean, calculation of the steady state error would become irrelevant in such cases. Okay, so we would be interested only in, I mean, calculating steady state errors if in the first place the system was stable. So I mean, if it was unstable, the response itself is going to show you that. Of course, over here we are not going to go to the response first and then the calculation of the steady state errors. We are doing it, I mean, doing the calculation first hand. I mean, we are starting off with the calculation of the steady state errors, but you should keep in mind that, I mean, sort of the you can say the analysis is valid. Validity of the analysis is only, I mean, possible, or rather is, it holds only if the system is stable. Otherwise, if it is unstable, you would find that the errors would be diverging. Steady state errors would, I mean, essentially be very much divergent, and there would be no requirement of calculating the steady state errors in the first place, right? So that would become irrelevant. So now coming back to where we were, if we, okay, I think time has slightly been exceeded. I'll just, I mean, give a bit more hint and then we'll continue in the next class. So if you have a type 1 system, say a first order type 1 system where the transfer function is 1 by s, okay. So now what would be your position error constant? If you are applying a step input, what would be your position error constant value?
Infinite.
Infinite, right? And hence what would be the steady state error value?
Zero.
It would be 1, yes, 1 by infinite,
Zero,
whatever, 1
zero.
by, yes, it's going to be equal to 0. So given a type 1 system that has a transfer function of open loop transfer function, of course I'm referring to 1 by s, you find that the steady state error is equal to 0. Similarly, now type 1 system with the second order transfer function, say 1 by s whole into s plus 1, okay. So again, what would be your kp value? Position error constant,
Infinite.
transfer function 1 by
Infinite.
infinite again, and ess is equal to 1 by infinite, which is equal to 0, right?
Yeah.
So we would be, by using different, I mean, type 1 transfer functions, you can check that the steady state error is essentially going to be equal to 0 if you are applying a step input to such a system. So that is why now, coming back to my initial claim, that is the type of the system is all important, meaning that if I have a type 0 system and I'm applying a step input, I know essentially that even if it is a 7th order system with, I mean, the rest of the terms being, I mean, there, and there are, I mean, zeros as well, poles as well as zeros, say several poles and zeros, just by looking at the type of the system, I would be able to predict what the steady state error is going to be, right? So that is why the type of the system is that much important, and the definition of the type actually takes into account the open loop or forward path transfer function of the system and the
Ma'am, could you repeat the discussion on the type 1 system? Mine, there was a net issue. I was,
okay.
it is not.
Type 1 system means, say for example, first order type 1 system example is 1 by s, right? 1 by s means kp will be equal to, now limit of s tends to 0,
Infinite.
1 by s infinite, and ess will be 1 by infinity, which is equal to 0.
Zero. Yes, yes.
Okay. Similarly, if it is a second order but type 1 system, so 1 by s into whole into s plus 1. Okay, so again, what will kp be? Limit of s tends to 0, 1 by s whole into s plus 1 will again be infinite, isn't it? So,
Yes.
so ess will again be equal to 0. So if it is a type 1 system, whatever be the order, you can take different order type 1 systems, you would be able to see that the steady state error will essentially be equal to 0, given that we are doing the analysis with respect to only a step command, right? Similarly, you would, I will not extend too far. We would be continuing in the next class because you will also tire out. We would be able to do a similar analysis for a velocity command, that is a ramp command, as well as an acceleration command. So we would be able to see that for type 0, type 1, type 2, etc. systems, the your error constants can be, respective error constants can be calculated, and hence the steady state errors can also be calculated, and based on that, there is, you will find in every book there, I mean, most of the standard textbooks, you would find that there are tables which give you the um, which give you the nature of the not nature, the value of the steady state error to be expected. We'll do this in a bit more detail in the next class that we have, right? So right now I'm stopping this presentation. You can go through whatever has been done, and we'll be continuing in the next class. So the next class, do you have anything on Wednesdays in the morning? Wednesday, okay. Wednesdays in the morning, 11 to 1 Wednesday.
On 25th.
You have class or not? I cannot understand. I don't get you.
Timing is not fixed on.
Okay. Okay. In any case, we'll stick to the Friday 11 to 1. Okay. So if there is some, any other thing that I want to do, I'll let you know. But let us say that the next class will be from 11 to 1 next Friday. Okay. So before everybody leaves, can you, I'll tell you something, that is, I will actually take the attendance today just to, make sure that I have the correct attendance sheet and all that. And also, please, those of you who are still there, please tell me if you are there, and also just whether you were present in the previous class or not. I'll just try to call the names in the orders that they appear on my sheet. Ankit Jaiswal, are you there?
Yes, ma'am. Previous one.
Okay, previous one you were present. Okay. Right. Kaushik Maji?
Yes, ma'am. Present in both.
Both classes. Okay. Okay. Then Shapnil Kisku? Shapnil? Okay. We'll keep that as it is. Dipten Marti? Trina Vishwas? Muhammad Ali Hamzan? Alak, what's your name? Alak Janri Murmu? Rajkumar Kanwar? Mohammad Iqbal? Ankush Ghosh? Yusuf Ali? Arman Hussain? Sahil Poddar? Parvez Musharraf? I hope you can hear me. There's a lot of background noise. Okay. Ritam Kamaru? Dipankar Singh? Ghulam Dipankar Singh, Ghulam Mojadid Alam, Shourav Das, Shobuj Mondol, Bikash Kumar Barnwal, Somnath Paul, Arijit Paul,
Yes,
Surujit.
ma'am.
Arijit, are you?